Hi. So in this new episode, we'll discuss the first solution concept called Nash Equilibrium. Okay, so that's basically the very first solution concept, and which is the simplest one that we can discuss together. Okay, and that and Nash Equilibrium is very powerful in predicting some behaviors and the equilibrium outcomes of the strategic games or the simultaneous move games. Okay, so now let's begin with some definitions of the some notations for the Nash equilibrium. Okay, so let's say if we have a set for all the players from 1 to n, okay, which is the set of the players, and we call that we have the action profile, which is the which is the Cartesian product of all the AJs. So J is element from set n. So and we denote the typical element from this action profile as this little a. Okay, so this should be a vector, but we just use this a to denote this vector for to indicate all those to indicate a element for the from the action space. Okay, action profile. Okay, so namely it means that this a should be should has some values, right? So in a row which is from a1, a2 up to a. Okay, so that's an action profile or an outcome, right? Okay, so and I is in the set of n. Okay. Okay, so and we use another very useful notation to denote the opponent of the player I. Okay, so that's essentially a minus I. Okay, so a minus I is from a1, a2 up to all the way to a I minus 1, and we skip ai, then goes to a I plus 1, and so on and so forth, and all the way to a, right? So that vector denotes the action profile, but excluding the action from player I, right? So that denotes the actions for all the other players. So or equivalently, this A should be AI and A minus I, right? So that's the action profile or the outcome of the game. Okay, so we have another useful notation. It's called the best response correspondence, and so a correspondence is analog to the function, but actually in a correspondence we can have a not only a one-to-one map, but it's actually a one-to-many map. So it's what we can input a value x into this sort of a function, or we call this correspondence, but the output is actually a set of some values. Okay, so it's not a number, so it's a set. Okay, so that's called the correspondence. So we have this, we define this best response. Okay, correspondence. All right, so we the input is some sort of x, okay, and the output x is a set. Okay, okay, so if we have this, so if this is a function, okay, fx, then we can have something like this, right? But if this is a correspondence, so this would be a set, right? So when we input any value for x, then the output is a set. Let's say it has a range. So the shaded area in between of those two lines would be the correspondence. Okay, so the best response correspondence would be something like this. Okay, so the definition is that for the player I, the bi, so given the input of a minus y, a minus I, so this means that given all those actions from the other players, then the best response for player I would be a set. So collecting the AIs from the capital AI, okay, from the space, and some requirements for this AI such that if the other players they play A minus I, then this player plays AI, then this action profile is weakly preferred. Then if other players playing A minus I, then this player is playing AI prime. So this AI prime should be true. So this preference should be true for all the AI prime, right? So the AI prime means all the other values, all the other possible actions in this action space AI, right? Instead of this AI. Okay, so that's true for all AI prime in AI. Okay, so that is essentially the meaning of this best response. That's very straightforward, right? Because this player I is playing his or her best response given other players' actions A minus I, right? So this is giving the highest utility or the most preferred actions or the preferred outcome, right? So in terms of the utilities, then we can define this in with U's, right? So U A minus I AI. So this is greater than or equal to the utility of A minus I AI prime, right? And for all the AI primes. Okay, so what is a Nash equilibrium? So essentially, Nash equilibrium is an action profile where everyone's action is the best response given other agents' actions, right? So it means that everyone in this equilibrium, in this steady state, is playing their best response given all the others players' actions. So everyone is actually is acting using the best response, right? Okay, so let's formally define a Nash equilibrium as our very first solution concept. So a Nash equilibrium, okay, is a profile, of course, right? So it's an action profile, A star, okay, of actions. So for which we have the requirement for that is AI star is an element of the best response for player I given all AI A minus I's, right? And this is true for each player. Okay, it has to be true for each player to make this solution concept. Okay, so so intuitively it means that we use NE for Nash equilibrium. So Nash equilibrium is an action profile, okay, where everyone's action is best response given other agents' actions. Okay, so those other agents' actions in turn are also the best responses of their own, right? Okay, so they're simultaneously best responses of each other's actions. Okay, so that's the definition, or that's this is also a interpretation of the Nash equilibrium. Okay, so now let's go back to the example that we have from the previous episode. Is that we using the famous example in the prisoner's dilemma, such that we have two players. They can either playing defending or confessing, right? D or C. Okay, have the same action space. Okay, so we have 3-3, and 0, 4. Okay, 4, 0 symmetrically, and 1, 1. Right. So, and remember what we did previously is that let's fix the action for the player 2. Let's suppose if player 2 is playing D. So in this case, player 1 is playing C to get this 4, right? So that's a sort of a best response for player 1. And if player 2 is playing C, then we can see from this table is that player 1 is playing C again. Okay, and symmetrically, maybe we just do that, right? So again, so if player 1 is choosing D, then player 2 is choosing C for sure, choosing to go for this 4. And player 1, if he's playing C, then player 2 is playing C again to get this 1. Okay. All right. So the Nash equilibrium here is this in this corner. So namely, two players are both playing C. Okay. So why though the other two, this one and this one, those who are not Nash equilibrium? So the reason is that in the case, let's suppose if player 2 is playing D and player 1 is playing C. So this is a best response for player 1. But we can see that if player 1 is playing C, then actually here, player 2 should choose C, right? So this D here, to get this 0, this D is not best response for player 2. So it means that this 0 or this D here is not a best response. It's not the sort of the ideal action that player 2 should be choosing, right? So this one and this one, they're not best responses for the other player, okay? So we can only have one Nash equilibrium or one pure strategy Nash equilibrium that we can define later for the pure strategy. So we have that only one pure strategy Nash equilibrium here is that both players are choosing C and each of them gets 1 for the utility, right? So namely C is a element of the, as we said, so best response correspondence is not a one-to-one map or one-to-one function, so it can output some values to form a set. So this C could be one element for the from the best response correspondence set, right? Okay, so if player 2 is choosing C, then player 1's choice C is in the best response, right? And of course, symmetrically, it is true for the other player, right? So if player 1 is choosing the C, then player 2's choice of C is in the best response for the player 2 themselves. Okay, so choosing C, and C is a pure strategy Nash, right? Nash equilibrium. And later we'll define what does the pure strategy mean, and we will show some more interesting games and some extensions for the mixed strategies and Nash equilibrium, right? Okay, so that's basically the introduction to the first solution concept called Nash equilibrium, and that shows the very interesting prediction for the players how to behave or how to choose their optimal actions given the simultaneous move game or the strategic game, right? Okay. And later we'll show the existence for the Nash equilibrium by using the Kakutani's fixed point theorem and to make some rigorous proofs. Okay.